Hi everyone, welcome to a continuation of the video that was presented before on buffer solutions. Now to refresh our memories, the problem was all about a buffer solution that contains 10.0 grams pyridine and 15 grams of its conjugate acid per 1 liter of that solution. Now the second question for this specific problem in this video that we'll try to solve is what will be the pH of the solution if 10 ml of a 2.00 potassium hydroxide, that is 2.00 molar potassium hydroxide, is added to 1.00 liter of the buffer solution that was mentioned earlier. Now you have to use the ICE chart to solve, which means initial, change, and equilibrium, which we also used in the previous video. So we will now try to see what happens when a base, specifically a strong base, is added to the buffer. Will it rather increase or decrease the pH of the buffer solution? Alright, so the first thing that we need to do at this point is for us to identify how many moles of the added strong base will interact with the buffer solution. So we need to take note or to calculate how many moles of the hydroxide anion will be taking part in the reaction. Now we will not be including the potassium ion because it's a spectator ion. Spectator ions are the ions that don't actually really do a big role in the reaction. So we don't actually include them in the calculations. So to calculate for the moles of the hydroxide and ion, we start with the concentration. That's 2.00 moles per liter. Then multiply that with the volume of that solution, which was 10 ml. So we converted milliliters or ml into liters. So if you still have a problem doing that, you might want to have some more practice in doing some conversions before you proceed with the problem. So we now have the moles of the hydroxide and ion. So from the previous video, we already know the moles of our buffer species, and these are the following. The moles of our pyridine is 0.126 moles, and the moles of its conjugate acid is 0.187 moles. So we'll be needing these moles to see the next part of this solution. Okay, so the next step is for us to have an idea what will happen in the solution when the strong base is added. So we have here the equation for that, showing only the species that will partake in the reaction, meaning not including the spectator ions. So we have here the conjugate acid of the pyridine, of course, will react with the added base in the form of the hydroxide ion, which will then form back your pyridine and of course water as one of the products. So at this point, we'll be using the BCA chart, or the before, change, and after, to take note of the changes in the number of moles of our species. So let's do that. Alright, so as what we have calculated before, these are the number of moles of the species involved, the hydroxide and ion, the pyridine, and of course the conjugate acid form. So of course, initially or before the reaction, we have 0.187 moles. Remember, these are moles for the BCA chart. We're using moles, not molarity, alright? So 0.187 for the conjugate acid, which will react with 0.0200 moles of the hydroxide upon adding the strong base. And of course, it will result to 0.126 of our the pyridine, and we don't have any value for the water since we don't include water in the equilibrium equation. Okay, any pure liquid or any pure any element in its pure form is not included in the equilibrium equation. All right. So for the change, of course, the addition of the hydroxide ion will bring a change of minus 0.02 for the conjugate acid. That's minus 0.02 as well, as it will be consumed for the hydroxide, and of course that's plus 0.0200 moles for the pyridine, since it's in the product side. So after all of this, we'll then simply do the algebra. That's 0.167, of course 0 for the hydroxide ion, and 0.146 for the pyridine. So we now have the number of moles of the species that we are trying to study after the addition, or after adding your strong base. So what is our next step will be to calculate the molarity of this species so that we will be able to use them for the ice chart. So let's do that. Okay, so as I have mentioned before, we will be calculating for the molarity of the species after the reaction has taken place. But remember, before you do that, never forget that the volume has now changed. From the initial 1 liter, you have added 10 milliliters of the base. So the final volume is now 1.010 liters. Now this is the added volume of the base, 10 milliliters, which we simply converted into liters to make the unit uniform. Okay, so we have here the calculation of the molarity of the pyridine. That's 0.146 coming from here. Remember, that's the after. Divided by the volume of the solution, total volume, that's 1.010 liter. So that's equal to 0.145 moles. So that's the final number of molarity of the pyridine in the solution. So let's do the rest of the species. Okay, so we now have calculated the final molarity of the pyridine and its conjugate acid after the addition of the strong base. So that's 0.145 molars for the pyridine and 0.165 molars for your conjugate acid. So remember, the value of the moles here was calculated earlier from the BCA chart, taking note of the addition of the strong base, and of course, taking note also of the total final volume. So after knowing this, we now go to the ice chart. Okay, so there is our ice chart. Remember, I stands for initial change in equilibrium. So this is again the equation of the species of the in the buffer solution that will be important at this point. So we now have calculated the final molarity of the species of the pyridine and its conjugate acid after the addition of the strong base. Okay, so we have here 0.145 for the pyridine and 0.165 for the conjugate acid. Of course, 0 for the hydroxide because it was used up in the reaction. So of course, the change will be represented by the x. So that's negative x for the pyridine, plus x for the conjugate acid because it's in the product side. Okay, so for the equilibrium, we have 0.145 minus x and 0.165 plus x for the conjugate acid. Of course, x is for the hydroxide ion. So we simply have to use the equilibrium equation to solve for x. Okay, so let's do that. Alright, so our equilibrium equation is the Kb is equal to the concentration, or rather to the product of the concentration of the conjugate acid multiplied by the concentration of the base, the hydroxide and ion, divided by the concentration of the pyridine. So that is the product of 0.165 plus x and x divided by the 0.145 minus x. Now remember, a very key point in this part of the solution is we have to remember that x here in terms of the value is negligible in comparison to the value 0.165 and 0.145. Now if you still have some problems with that, you might need to review again on the chemical equilibrium concepts why that x should be considered as negligible at this point. There's a specific rule for that, which will not be any more discussed here for the limit of the time being, right? So a very simple idea is it will really simplify the calculation, because if that x will still be considered, it might give us a quadratic equation which will take us a longer time to calculate. Okay, so since x is negligible, this will simplify into Kb, which is 1.40 times 10 to negative 9, and this was given in the problem earlier, and that is equal to the product of 1.65 times x divided by 0.145. Remember, these values here are in the molarity unit. Okay, so we simply solve for x. So this rearranges into 0.165x is equal to 1.40 times 10 to negative 9 multiplied to 0.145. Remember again that the units here are in molarity. Alright, so x is equal to 1.23 times 10 to negative 9 molars. Okay, so let me just put in the molar. Alright, so there's the unit so that you will not be confused, and always remember the value that we are using here are in molarity. Alright, so 1.23 times 10 to negative 9 molars, and that is of course x, and in our ice equation x refers to the concentration of our hydroxide ion, which can give us our pOH. So to solve for our pOH, we simply get the negative logarithm of this concentration. Alright, so again, the pOH is the negative logarithm of the hydroxide ion concentration. So that is equal to negative logarithm of 1.23 times 10 to negative 9 molars, which was our X. So this is equal to 8.91. So that is the pOH of the buffer solution after adding the strong base. Now, we simply need to calculate for the pH using the simple equation that we had introduced before, and that is pH is equal, no, rather pH plus pOH is equal to 14. So neutral pH is 7, neutral pOH is 7, so that's a total of 14. Alright, so we simply rearrange that and solve for the pH. Alright, so the pH is, so pH is equal to 14.00 minus 8.91, which is our pOH, and that is equal to 5.09. So the pH of the solution after adding your strong base is 5.09. Now, if you compare that from the previous video, which we calculated the pH of the buffer solution originally is at 4.97. So this means that after adding the strong base, obviously, we have increased the pH of the buffer solution. Alright? So I hope you've learned in this video tutorial. Thank you for listening and continue learning.